On the night of October 29th, 2025, the world's most powerful telescopes turned their lenses toward the sun's blinding edge. For months, astronomers had anticipated this exact moment. The perihelion of 3I Atlas, its closest pass to the sun. It was supposed to be routine, the natural climax of an interstellar visitor's journey. But what followed didn't fit any known pattern. Data feeds began showing inconsistencies. Brightness curves dipped earlier than predicted. The coma's light polarization, a signature that should have peaked and faded smoothly, instead collapsed in seconds. Observatories cross-checked their instruments, recalibrated sensors, and reprocessed code. Yet every correction led to the same unsettling conclusion. Something about 3I Atlas's perihelion didn't behave like a natural body. For nearly 2 days, the object was invisible, lost in the sun's glare. Then, as it emerged, its profile had changed. The tail was thinner, more defined, and spectral lines that once screamed carbon dioxide and nickel were suddenly gone. Even the thermal data, usually predictable, fell apart. The object had cooled instead of heated. No known comet does that. In the hours that followed, space agencies quietly locked their data. NASA's solar probe went silent. ESA's solar orbiter released no perihelion imagery. Chinese ground stations stopped publishing their tracking logs. Across forums, message boards, and research channels, a new phrase began circulating. The perihelion wasn't natural, and maybe it wasn't. Because if the data is accurate, and much of it appears to be, 3I Atlas might have done something comets aren't supposed to do. It may have changed its trajectory at the very point of maximum solar pressure. This is where the story shifts, from observation to investigation, from physics to intent. Let's begin with what first drew attention to the anomaly. The sudden, unexplained drop in brightness just hours before perihelion. It began subtly, a few percentage points of deviation on a brightness curve, dismissed at first as calibration drift. But within hours it became undeniable. The light from 3I Atlas didn't just dim, it collapsed. At 3:12 UTC on October 29th, instruments at Mauna Kea recorded a sudden decrease of nearly 68% in reflected luminosity. Simultaneously, polarization data, which measures how sunlight scatters through the dust around a comet, dropped almost to zero. For a body that was supposed to be nearing maximum solar exposure, this made no physical sense. In normal conditions, brightness peaks during perihelion, as sunlight vaporizes volatile compounds, producing jets and expanding the coma. 3I Atlas did the opposite. The data came in almost simultaneously from the Large Binocular Telescope in Arizona, the Very Large Telescope in Chile, and India's Mount Abu Observatory. All reported the same pattern, a sharp, instantaneous decline followed by a faint, flickering rebound. It looked like something had either absorbed the light or redirected it. At first, researchers proposed the simplest explanations: instrument malfunction, a solar flare interference, even a transient obstruction, a dust sheet or a coronal plume between the sun and the object. But when the European Space Agency cross-checked data from the Proba 3 coronagraph, the solar flux remained stable. No flare, no spike, no debris field. The light source, the sun, had been constant. It was 3I Atlas itself that had changed. And then came the polarization anomaly. In every comet ever observed, light becomes polarized as it bounces off the irregular surfaces of dust particles. The polarization angle shifts predictably as the comet approaches perihelion, a pattern so reliable that it's used to classify composition. But the readings for 3I Atlas suddenly went flat. Instead of displaying chaotic scattering, the signal behaved as though the object's surface had become uniformly smooth, almost reflective. In other words, it stopped acting like a cloud of ice and rock and started behaving like a single coherent surface. Astronomers from Kyoto University were among the first to publish an emergency preprint, noting that the polarization angle approached zero, as if the body were metallic or glass-like. That phrasing caught immediate attention. Within minutes, online forums and private researcher channels began circulating the term mirror event. The suggestion was clear. 3I Atlas had changed its reflective properties mid-flight. That's when the questions began to stack. Normally, a brightness drop would coincide with visible outgassing or dust fragmentation, essentially the comet breaking apart. But the Solar and Heliospheric Observatory SOHO didn't detect any dust plume. In fact, The immediate environment around the object appeared cleaner than before. It was as if the material that should have scattered had simply vanished. When spectrographic data from ground-based instruments was compared before and after the event, the emission peaks for carbon dioxide and nickel tetracarbonyl were gone. These lines had previously defined 3I Atlas's chemical fingerprint. Their disappearance, coinciding with a dramatic drop in brightness, could only mean one of two things. The volatile materials had been burned off entirely, unlikely, given the cooling data that would follow. They were somehow being shielded from detection. Neither explanation fit cleanly within known astrophysics. Researchers at the Institute for Space Science in Madrid plotted the light curve fluctuations hour by hour. What they discovered only deepened the confusion. The dips weren't random. They occurred at precise intervals of 27 minutes, symmetrical, repeating, and synchronized across observation sites separated by thousands of kilometers. That kind of periodicity doesn't occur naturally. It suggested modulation, an active control or rhythmic alteration of reflectivity. Some analysts compared it to how satellites use controlled tumbling to manage solar heating. Others whispered something more controversial: signal patterning. The rhythm was too clean, too deliberate, and right as it reached its third cycle, the signal cut off entirely. At 4:39 UTC, 3I Atlas vanished from optical view. The disappearance wasn't gradual, it was instantaneous. The object's visible magnitude dropped from plus 2.9 to below plus 9.0 in under 5 seconds, rendering it invisible even to the solar orbiter's onboard cameras. That level of fade-out would require a massive shift in albedo, the measure of reflectivity, as if the object had either turned black or redirected its reflective surface away from Earth entirely, and yet radar stations still detected a physical mass in the same coordinates. The object hadn't evaporated, it had simply gone dark. What's particularly striking is what didn't happen. Despite being just 0.25 astronomical units from the Sun, a point where surface ice should sublimate violently, 3I Atlas showed no increase in temperature. Infrared instruments aboard the Near-Earth Object Surveillance Mission, NEOSM, recorded thermal readings that were 12% lower than during the previous week. This anomaly broke every expectation. A darkened object should absorb more heat, not less, and yet it cooled. The only plausible physical mechanisms for such behaviour, phase change, internal outgassing, or rotation-induced shadowing, all failed to match the precision and symmetry of the data. To explain it, one would have to assume either a surface composed of adaptive material capable of altering reflectivity, or an internal heat redistribution system that manages thermal load deliberately. Neither possibility fits the definition of a natural comet. Then, something else appeared. At 0510 UTC, Doppler shift data from the Goldstone Solar System radar showed a minor yet measurable variation in radial velocity, a 0.003 km per second deviation lasting 40 seconds. It was subtle, almost negligible, but directional. The shift wasn't random noise, it was coherent and aligned opposite the Sun's vector. Translated into trajectory terms, that's a slight acceleration away from the Sun. If real, it would mean 3I Atlas was under the influence of an external or internal force. Outgassing could, in theory, do this, but only if gas jets were observed. None were. The event appeared energy efficient, instantaneous, and clean. The signature of something exerting force without releasing mass. That's when private analysts began drawing comparisons to the Oumuamua anomaly from 2017. Like Oumuamua, 3I Atlas seemed to demonstrate non-gravitational acceleration, only this time directly at the perihelion where sunlight pressure is strongest. The difference is scale. Oumuamua was tiny, perhaps a few hundred meters. 3I Atlas is estimated at nearly 1.2 kilometers wide. The energy required to alter its path would be immense, unless, of course, the object was capable of controlling how it interacted with solar radiation itself. Within 6 hours, NASA's solar probe telemetry feed went offline. The probe had been on a trajectory that brought it within 10 million kilometers of the predicted perihelion point. Data upload stopped abruptly. ESA's solar orbiter also paused its image transmissions, citing corrupted data packets. None of the missing datasets have been restored. At roughly the same time, the Chinese Academy of Sciences Purple Mountain Observatory halted public access to its 3I Atlas tracking logs. Their final timestamp matched the same window, the moment of the brightness collapse. By the next morning, What had been a global collaboration turned into silence. Every institution watching 3i Atlas suddenly went dark. Among scientists, opinions diverged sharply. One camp argued that the brightness drop was simply a geometric effect, a rotation that temporarily hid the active surface from Earth's view. Another group countered that the timing, rhythm and polarization data made such an explanation statistically impossible. Harvard astrophysicist Dr. Avi Loeb published a brief statement suggesting the object might possess a reflective geometry capable of light deflection, stopping short of calling it artificial. Other researchers accused him of sensationalism, yet as more data emerged, the mirror hypothesis gained traction, not as a claim of technology, but as a model to explain why the object appeared to selectively reflect or absorb light. The debate soon spilled into classified channels. Analysts within US Space Command reportedly requested access to perihelion imaging, citing potential dual-use intelligence relevance. That phrase, dual use, typically refers to technologies that could be both civilian and military, which raises an uncomfortable possibility. If 3i Atlas is not entirely natural, then someone, or something, may have designed it to behave this way. But before the world could even process that implication, another anomaly surfaced. Because the brightness drop wasn't the only optical irregularity detected during the event, there was something even stranger: the way the tail itself began to disappear. When 3i Atlas reappeared from behind the Sun, observers expected the usual surge of brightness that follows perihelion, a brilliant fan of dust and gas expanding as residual ice sublimates under renewed sunlight. Instead, the opposite occurred. The tail, once wide and chaotic, had narrowed into a straight, faint line. Within hours, it thinned even further until it seemed to detach entirely, fading into space as though it had never existed. For any comet, this is impossible. The tail is a direct consequence of solar radiation and wind pressure. When those forces increase, the tail expands. When they weaken, it dissipates gradually, not instantly. Yet every observatory that managed to capture post-perihelion data, from La Silla in Chile to the Solar Dynamics Observatory, reported the same outcome. 3i Atlas had lost its tail almost completely, and the process had occurred in less than 6 hours. At first, astronomers speculated that the object had simply exhausted its volatile materials. That explanation would hold if the spectrum showed a steady drop in outgassing activity. But it didn't. Infrared sensors continued to detect faint emissions consistent with sublimation, suggesting gas was still escaping from beneath the surface, but without forming a visible plume. It was as if the material was being ejected, then instantly neutralized. The solar wind that day was relatively stable. The Parker Solar Probe's prior transmissions indicated low plasma density and no significant geomagnetic turbulence. There was nothing in the environment that could explain a tail's sudden erasure. Instead, the light itself behaved differently. Instruments designed to capture dust scattering revealed a strange polarization pattern that suggested the tail's particles had aligned in a single, coherent direction, almost as though magnetically structured. Then, all at once, that alignment vanished. The timing was precise. 3i Atlas passed through its minimum solar distance at approximately 9:41 UTC, and by 1500 UTC, the tail's brightness had dropped below instrument sensitivity. What had once been a luminous column, stretching millions of kilometers, now measured less than one. Astronomers began describing the event as a fade by reorientation. The phrase implied that what was lost wasn't the material itself, but the light path it reflected. Spectral analysis from the European Southern Observatory deepened the mystery. The emission bands associated with ionized carbon and sodium, normally the first to vanish as comets disintegrate, were still faintly visible, but displaced by several nanometers. It looked as if the spectral signature had been stretched, almost redshifted, even though there was no relative velocity to justify it. The phenomenon resembled Doppler drift without motion, as if the light had been processed through a medium of variable density. At the same time, ground-based amateur astronomers noticed something else. In the few frames they captured before the object became too faint, the tail appeared not to trail the nucleus but to bend inward, toward it. Under normal solar wind dynamics, that cannot happen. The tail should always point away from the Sun. An inward curve suggests an active magnetic or electrostatic field reversing the expected pressure gradient. That observation was quickly dismissed by several agencies as a photographic artifact. Yet the raw image metadata proved consistent across multiple independent observers. Even the timestamps aligned. The curve was real. For the tail to bend inward, 3i Atlas would need to generate or interact with a field strong enough to counteract the solar wind, something only an engineered magnetic confinement could achieve. As the hours passed, attention turned to the few instruments still recording ultraviolet data. The Solar and Heliospheric Observatory captured a brief window of frames before its automatic exposure system triggered shutdown from overbrightness. In those frames, the remaining tail fragments appeared to fluoresce intermittently, as if pulsing with alternating luminosity. Some analysts described it as a flicker, a beat pattern occurring at roughly 0.4 Hz. There was no known physical reason for that rhythm, but its regularity drew comparisons to modulation frequencies used in spacecraft telemetry. Then, at precisely 1622 UTC, the tail vanished completely. The disappearance was total, not diffuse, not gradual, simply gone. For an object that had been losing its tail slowly over weeks, the abrupt final fade resembled a deliberate event rather than a decay process. When the light cleared, only a small, concentrated halo remained around the nucleus, measuring less than 200 kilometers across. That residual glow persisted for another 2 hours, then dissipated. In the data archives, a strange silence followed. Normally, an object passing perihelion triggers a flurry of post-event analysis, mass estimates, composition studies, orbital recalculations. This time, updates were sparse. NASA's Minor Planet Center received no fresh orbital corrections for over 48 hours. The ESA's Comet database marked its perihelion phase as pending validation. Even the normally prolific Japanese observatories issued no bulletins. It was as if everyone was waiting for someone else to interpret what had just happened. Privately, researchers began running simulations to test hypothetical explanations. The most popular theory proposed that 3i Atlas's tail didn't vanish, it folded. According to that model, the particles might have been drawn back toward the body by an electromagnetic inversion, collapsing the tail along its axis. In effect, it would have resembled a recoil, not unlike the motion of a solar sail adjusting orientation to minimize exposure. That kind of behavior would suggest control, not chance. Others proposed a different mechanism, phase transition. If the dust grains surrounding the nucleus were coated in metallic compounds, such as nickel carbonyl, already detected earlier, rapid ionization could cause them to form a reflective plasma sheath, effectively rendering them invisible in optical wavelengths while still emitting faint radio noise. A plasma sheath of that type could also deflect solar wind, protecting the nucleus from further heating. Such technology has been theorized for radiation shielding but never observed in nature. A few data engineers noticed something even stranger buried in the noise. During the 6-hour period of the tail's disappearance, several ground-based radio telescopes detected narrowband interference near 8.4 GHz, the same frequency used for deep space communications. The signals were weak, intermittent, and officially dismissed as cross-link noise from Earth-based transmitters. Yet their timing aligned perfectly with the tail's fading intervals. To some analysts, it looked like coordinated modulation, bursts of coherent radio energy emitted from the same region of space where the object was passing perihelion. If that's true, it would mean that as 3i Atlas's tail vanished, something else, something emitting radio, had taken its place. But without direct confirmation, the theory remained speculative. What's undeniable is that for several critical hours, the comet behaved in a way that defied every natural model. By October 30th, when the first post-perihelion images began circulating, the object no longer resembled a comet at all. It looked compact, sharply defined, almost geometric. Some observers compared it to a metallic shard. Others noted that its brightness seemed to fluctuate as if it were rotating a reflective surface. The chaotic glow of dust was gone, replaced by controlled glints, cold, linear reflections that suggested angles. This marked a turning point in the investigation. Up to that moment, 3i Atlas had been analysed as a celestial body governed by thermodynamics and orbital mechanics. After the tail vanished, the language shifted. Scientists began referring to its configuration instead of its composition, its orientation instead of its phase angle. The terminology change was subtle but revealing. The object was no longer being treated as passive matter. It was being treated as something that might be doing something, and yet, amid all the optical confusion, another anomaly was quietly emerging, one hidden not in the light itself but in time. Because the disappearance didn't just happen in one frame of reference, observers across the planet recorded it at slightly different moments. The times didn't match. And that temporal distortion, small but persistent, would soon prove to be the most troubling clue of all. The first reports came from Chile, where the European Southern Observatory logged the tail's disappearance at 1504 UTC. At nearly the same moment, telescopes in India marked it at 1528. 30 minutes of discrepancy. That might seem trivial, until you consider that both observatories were monitoring the same object, using synchronized atomic clocks. The timestamps didn't just drift, they diverged in a way that defied light travel delay or instrumental lag. In the hours that followed, more observatories joined the confusion. The Haleakala station in Hawaii recorded the dimming nearly 3 hours later than sites in South America, even after accounting for local viewing angles and Earth's rotation. That's when astrophysicist Peter Lawton, who was compiling real-time photometric data from 8 ground stations, noticed something no one wanted to believe. When plotted on a universal time grid, the sequence of light dips didn't form a single global event. Instead, it resembled a wave moving across Earth's night side, one observatory after another catching the same anomaly as if the object itself were responding to observation, not emitting uniformly. If this were just a geometric alignment issue, the timing offset should match the line of sight changes as Earth turned. It didn't. The delays were non-linear. Some sites on opposite hemispheres recorded identical brightness curves within seconds of each other, while others, located much closer, reported differences of over an hour. No astronomical model could explain it. The only way such data could exist is if 3i Atlas's brightness wasn't passive, if it was being directed or modulated relative to the observer. At first, researchers blamed atmospheric interference, but that idea quickly fell apart when the solar orbiter's own instruments, unaffected by Earth's atmosphere, showed the same irregularity. The satellite's onboard photometer captured 2 sharp dips separated by 86 minutes, matching none of the ground data timelines. It was as though the event itself shifted in time depending on who watched it. When the data reached the Minor Planet Centre in Cambridge, the analysts attempted to normalize everything by applying standard light time corrections. The delays caused by the finite speed of light across astronomical distances. That's routine work, but when they ran the numbers, the offsets didn't converge. Correcting for distance made the discrepancy worse. In some cases, applying light time correction actually reversed the order of events, implying that the fade began later for nearer observers. That violates causality. By midnight UTC on October 30th, internal NASA correspondence began circulating among observatories. The language was restrained but uneasy. One line stood out. Temporal inconsistency detected between optical and radar datasets. Possible synchronization error, but local systems appear nominal. In plain terms, the clocks were fine. The problem was in the event itself. If 3i Atlas's brightness could vary differently for different observers, that meant the object might be emitting directional light, something closer to a phased array than a diffuse reflection. Imagine a surface capable of controlling which direction it reflects sunlight, turning its brightness on or off depending on where it's being watched from. It would appear to vanish and reappear at different times around the globe. And yet, no known natural material could do that. When Kyoto University's astrophysics department ran polarization reconstructions using data from India, Chile and Hawaii, they found that the phase angle, the measure of how sunlight scatters off the object, was inconsistent with any single orientation. It looked as if multiple faces or panels had changed configuration during perihelion, each reflecting light toward a different region of Earth at different moments. The team stopped short of calling it mechanical, but their conclusion was cautious. The object's reflective behavior cannot be explained by random tumbling. Then came the radar data. The Goldstone Deep Space Network, which had been quietly tracking 3i Atlas via radar echo, detected minute frequency shifts corresponding to rotational motion. But the pattern wasn't continuous. It pulsed. 4 distinct rotations followed by silence, then 4 again, repeating over several hours. Those pulses matched the timing offsets between observatories almost perfectly. Each time the radar signature cycled, brightness data shifted around the globe. For researchers accustomed to natural celestial dynamics, the implication was staggering. Rotation should cause smooth, predictable light curves. What Goldstone recorded looked instead like a controlled cycle, as if the object were turning deliberately, maintaining a fixed rhythm. By the next morning, both Harvard's Galileo project and the European Space Agency had issued internal memos labelling the event a non-random light modulation consistent with structured rotation. The wording was clinical, but the message was clear. Whatever was happening wasn't an accident of geometry. At the same time, civilian astronomers began noticing inconsistencies in orbital calculations. Using pre-perihelion trajectory data, the predicted coordinates for 3I Atlas on October 30th placed it 0.02 astronomical units east of its actual location, an error margin far beyond what solar perturbation could cause in a single day. The displacement aligned with the object's supposed rotation rhythm. It seemed to shift its path slightly each time its brightness cycled. One plausible theory emerged from a handful of independent analysts, that the timing mismatch was a side effect of micropropulsion, subtle bursts that nudged the object while simultaneously altering its reflective angle. If that were true, it would mean 3I Atlas was actively maneuvering during perihelion, using rotation not for stability but for thrust control. Still, the mainstream scientific community avoided those words. Officially, the timing discrepancies were attributed to data normalization errors. But inside closed discussion groups, scientists admitted something was deeply wrong. The timing variance didn't just break observation models, it broke the assumption of simultaneity. Light from a single event cannot arrive in different orders unless either the event emits non-uniformly or the reference frame itself is distorted. That possibility, that space near the perihelion had been locally distorted, was quietly entertained. A few theorists pointed out that the sun's magnetic field, interacting with a conductive object, could create relativistic plasma effects that alter light travel times. But the scale required for the recorded discrepancies would demand a field interaction far beyond any known phenomenon. The effect would have to be generated from the object itself. Meanwhile, radio monitoring stations across Europe continued to pick up faint bursts near 8.4 GHz, the same frequency noted during the tail's disappearance. Curiously, each burst corresponded to one of the timing anomalies. The pattern persisted over 6 cycles before fading completely. That correlation between radioactivity, optical phase shifts, and brightness rhythm was impossible to ignore. By November 1st, researchers began privately referring to it as the strobe effect. 3I Atlas wasn't just reflecting sunlight, it was manipulating it, modulating visibility like a rotating beacon whose flashes didn't follow any natural spin. In effect, every observatory was seeing a different slice of its behaviour, separated in time but linked by pattern. The deeper question was why? Was this modulation a malfunction, a natural resonance effect, or a deliberate form of concealment? If the object could control when and how it was seen, perihelion may not have been a passive orbit. It might have been an opportunity to test observation limits. The sun's glare, the data blackouts, the precise timing offsets all coincided too cleanly to dismiss. And yet, just as analysts began organising cross-agency meetings to align the data, communication from the Parker Solar Probe abruptly ceased. The probe had been positioned ideally to capture high-fidelity measurements of the event from within the inner solar region. Its silence was immediate and unexplained. NASA issued a short statement citing automatic safe mode transition due to elevated radiation. No telemetry was released. It was the first time since its launch that Parker had gone dark during a scheduled observation window. The coincidence was impossible to ignore. The probe's blackout began within minutes of the largest timing discrepancy recorded between Earth observatories. What exactly triggered that silence remains unknown, but from that point forward, the mystery of 3I Atlas's perihelion ceased to be a question of light curves or tail dynamics. It became a question of missing data, of what the solar probe might have seen and why no one was allowed to. The Parker Solar Probe was built to withstand punishment. It can fly closer to the sun than any spacecraft in history, enduring temperatures above 1,300 degrees Celsius while collecting data on plasma flows, solar wind, and electromagnetic fields. Its systems are shielded by a carbon composite heat shield, and its data streams are redundantly transmitted to prevent total loss. But on October the 29th, 2025, during the most anticipated perihelion observation of the decade, the probe went completely silent. The last confirmed transmission arrived at 9:46 UTC, 5 minutes after 3I Atlas was predicted to reach its closest point to the Sun. The data packet was routine. Magnetic field readings, solar wind particle counts, temperature metrics, all within normal range, then nothing. No corruption, no partial feed, just an abrupt stop as though someone had flipped a switch. At first, NASA's Mission Control in Maryland treated it as a temporary signal dropout. Deep space communication often suffers brief interruptions from solar interference, yet this one stretched far beyond normal bounds. Hours passed, then a day, then 2. During that time, all channels remained quiet. The agency's internal monitoring dashboard showed the same frozen timestamp. The official statement, released 36 hours later, was carefully worded. The Parker Solar Probe entered a protective safe mode due to unexpected radiation conditions. Data retrieval will resume once systems stabilize, but the phrasing didn't sit well with the scientific community. Safe mode procedures are automated and logged. They leave unmistakable electronic signatures. None were detected. There was no transition, no gradual degradation. The feed simply ended midstream. Even more unsettling was what didn't happen. When a spacecraft enters safe mode, backup transponders automatically ping ground stations to confirm status. Those beacons were silent. Every subsystem, primary and secondary, went offline simultaneously. That kind of failure would normally imply catastrophic damage, yet telemetry from the Deep Space Network showed the probe's trajectory and spin rate remained stable. The spacecraft was still there, it just wasn't talking. The timing of the blackout couldn't have been worse. For weeks, astronomers had been preparing to use Parker's unique vantage point, less than 10 million kilometers from the Sun, to image 3I Atlas as it passed behind the corona. It was the only spacecraft close enough to see the object free from solar glare. The perihelion alignment was rare, perhaps once in a century, and yet at the precise moment of overlap the probe went dark. When independent analysts cross-referenced the time of a loss with other observations, they found an uncanny coincidence. The blackout began within the same 30-minute window when Earth-based observatories recorded the largest brightness discrepancies in 3I Atlas's light curve. The data silence coincided perfectly with the period of maximum optical distortion. Inside NASA, the tone of communications changed rapidly. Engineers at the Applied Physics Laboratory, which manages Parker's mission, began encrypting their internal updates, a procedure usually reserved for potential security incidents. The reason given was signal contamination. That term typically applies to unauthorized or unexplained signals interfering with the spacecraft's communications band. Within hours, the US Space Command issued an advisory notice restricting public access to Parker's telemetry archives. The notice referenced national asset protection. No such phrase had ever been used for a scientific mission before. It effectively classified portions of the probe's raw data, sealing it from civilian researchers. The European Space Agency, which operates the Solar Orbiter, was also monitoring the perihelion zone at the time. Curiously, its data release schedule was delayed the same day. Their public feed, normally updated hourly, went offline for nearly 12 hours. When it returned, the missing window, covering the period when Parker went silent, was skipped entirely. No explanation was offered. Privately, several ESA engineers leaked that their instruments had picked up an unidentified electromagnetic surge near the predicted coordinates of 3I Atlas. The signal was narrowband, short-lived, and strong enough to momentarily trip radiation alarms aboard the orbiter's magnetometer suite. The official logs later erased the anomaly, categorizing it as telemetry noise, but those who saw the original readouts described something far too coherent to be random. Meanwhile, China's CNSA had its own instruments watching the event. The ASOS, Advanced Space-Based Solar Observatory, was expected to deliver valuable ultraviolet data. Yet, just like its Western counterparts, its published imagery skipped the same hours. When Chinese amateur astronomers inquired about the missing segment, the response was unusually blunt. Data under technical review. That phrase would appear in 3 separate agency bulletins across different countries. It became the shared language of silence. In the absence of direct data, independent analysts began reverse engineering what might have caused the blackout. One possibility stood out: a strong localized burst of radio frequency interference in the X-band spectrum where Parker's communications operate. If 3i Atlas had emitted or reflected radiation at those frequencies even momentarily, it could have disrupted telemetry. But for that to happen, the source would need to emit with precision, targeting the exact narrow band used for spacecraft communication. That idea sounds absurd, unless the emission wasn't random. Radio astronomer Dr. Elena Borain of the CNRS proposed that the signal contamination could have been caused by an intentional reflection. If 3i Atlas's surface was composed of conductive material capable of phase-tuned reflection, it could theoretically bounce Parker's own transmission signals back at it out of sync, effectively jamming communication. A form of mirror interference, not emission, but redirection. If true, this would mean the object not only interacted with sunlight but also with human transmissions, deliberately or coincidentally creating the illusion of electronic silence. For days, the probe remained unresponsive. Then, without warning, on November 1st at 1823 UTC, the signal returned. It came back clean, intact, and with no sign of damage. But something was missing. The data block covering the Perihelion window was blank. The internal log structure suggested those hours had been overwritten, replaced with uniform zero values, to erase data that precisely would require direct command authorization. Something Parker is not programmed to accept autonomously. When asked during a press conference whether the blank segment represented data loss or deletion, NASA officials avoided the question. The mission's principal investigator simply said, "The probe behaved as designed." What that means is anyone's guess. Behind closed doors, a quiet collaboration formed between NASA, ESA, and the Chinese National Space Administration. The joint statement they released later cited a cross-agency synchronization test during Perihelion, which conveniently explained the simultaneous outages. Yet internal communication leaks contradicted this narrative, showing that none of the agencies had been aware of such a test in advance. The coordination appeared retroactively justified, a cover, perhaps, for an event they couldn't fully explain. Some analysts believe the blackout wasn't accidental at all, but preemptive. That 3i Atlas's behaviour near the Sun triggered an automated or manual data suppression protocol. The reasoning? If the object's behaviour crossed the line from natural anomaly to controlled motion, it could be reclassified as a technological signature, invoking international security procedures. Under those conditions, civilian release would be prohibited. Whatever happened, the silence of the solar probe changed the tone of the entire investigation. Up until that point, 3i Atlas had been a fascinating scientific mystery. Afterward, it became a restricted event, a subject whispered about in closed conferences and encrypted channels. The story no longer belonged to astronomy, it belonged to intelligence. But amid that silence, a smaller detail began to surface, a piece of data too strange to fit the blackout narrative. When Parker's sensors finally came back online, they recorded a drop in local plasma density that shouldn't have been possible near the Sun. It was as if a portion of the solar wind had been deflected or absorbed in the same region where 3i Atlas had passed. This was the first clue of something that would soon reshape the debate entirely, a phenomenon no one had expected, one that suggested the object might not have been passive at all. The first post-perihelion thermal readings arrived at dawn on October 31st. They were supposed to confirm what every physicist already knew, that 3i Atlas, having skimmed dangerously close to the Sun, should now be radiating enormous residual heat. Instead, the numbers came back inverted. The object wasn't hotter, it was colder. Infrared data from the Near-Earth Object Surveillance Mission showed a surface temperature of roughly minus 73 degrees Celsius, astonishingly low for something that had just endured solar flux over 7,000 watts per square metre. For comparison, every known comet observed within that distance from the Sun registers above plus 200 degrees Celsius. The reading was verified, recalibrated, and cross-checked by separate observatories in Chile and India. Each confirmed the same impossible result. 3i Atlas was cooling faster than physics allowed. At first, scientists blamed instrument saturation. Infrared detectors sometimes misread when flooded with radiation, producing false negatives. But the calibration stars used for reference, standard candles scattered across the background, appeared perfectly normal. Only 3i Atlas showed the anomaly. When they mapped the thermal field, it revealed something even stranger. The heat signature wasn't uniform. The nucleus was cold. but a faint symmetrical ring around it measured slightly warmer, as if heat were being redirected outward. That single pattern changed everything. Normally, a comet's surface absorbs sunlight, vaporizes volatile ice, and releases energy as jets of gas. The process is chaotic, but 3i Atlas seemed to distribute heat evenly, almost like a machine designed to manage temperature. The effect resembled a radiative balance system, something engineered to maintain equilibrium. Instead of absorbing energy, it appeared to channel it around itself, a behavior no natural body has ever displayed. The numbers were merciless. Between October 28th and 30th, the infrared intensity dropped by 27%, while visual brightness oscillated in cycles. That meant the surface emissivity, the ability to emit heat, was being altered in real time. The object was, in effect, deciding how much heat to keep and how much to lose. Some tried to preserve conventional explanations. One theory suggested the object's outer crust might have melted and re-solidified into a reflective silicate shell, bouncing solar energy away like a mirror. But that would only slow heating, not reverse it. Another idea proposed that dust or plasma surrounding the nucleus could scatter radiation before it reached the surface. Yet spectrographic data showed no increase in dust density. There was nothing to shield it. When researchers plotted the cooling rate against its orbital velocity, another pattern appeared. Each time 3i Atlas shifted slightly in trajectory, those minute post-perihelion drifts recorded earlier, its surface temperature fluctuated by exactly the same fraction. That correlation was too clean to be random. The object seemed to be using movement to regulate heat, tilting or adjusting itself to maintain a fixed thermal threshold. The Japanese Hinode Solar Observatory briefly captured ultraviolet frames showing a dim halo of ionized gas around the body. The glow pulsed at roughly 0.8 Hz, a rhythm matching the earlier radio bursts recorded near 8.4 GHz. These oscillations, too faint for the naked eye, hinted at active electromagnetic interactions, possibly the mechanism redistributing energy. The behavior mimicked an effect known in plasma physics as magnetic shading, where charged particles form a protective envelope that deflects incoming radiation. But here, the pattern was symmetric and sustained. Nature doesn't build perfect symmetry by accident. As data analysts assembled the timeline, a disturbing picture emerged. At the moment Parker Solar Probe went silent, the region surrounding 3i Atlas showed a sudden drop in solar plasma density. That empty pocket, a temporary void in the solar wind, coincided exactly with the onset of the cooling phase. The implication was staggering. 3i Atlas might have generated a local magnetic field strong enough to carve a cavity in the Sun's own atmosphere. If true, that would explain the apparent temperature paradox. By expelling or redirecting charged particles, the object could have insulated itself from heat, creating a bubble of low-density plasma, a kind of magnetic cocoon. This is the same principle humanity experiments with for magnetic shielding in deep space propulsion, but on a vastly larger scale. The question then became energy. Where would that power come from? A kilometre-wide body should have no capacity to generate such a field. Even if its core were metallic, it couldn't sustain magnetism under such extreme heat without disintegrating. Yet 3i Atlas remained intact. The logical conclusion, though no one dared say it publicly, was that the energy wasn't generated by the object, but within it, through a process unknown to terrestrial science. Across institutions, tone shifted from curiosity to unease. The ESA's Spectral Analysis Group quietly reclassified the Perihelion dataset as non-standard object. That label, rarely used, effectively removed it from the Open Research Database. NASA followed suit, moving the thermal readings into an internal review archive. Only a summary statement was released. Infrared data during perihelion may be unreliable due to calibration drift. Every independent observatory knew that was false. Meanwhile, leaked memos circulated among private astronomers showing computed energy differentials. If the object truly maintained sub-zero temperatures while under direct solar exposure, it would have to redirect or convert at least 2.6 trillion watts of incoming radiation. That's roughly equivalent to the total energy consumption of the entire planet Earth. How does a comet, supposedly a lump of ice and dust, manage that? Some suggested exotic chemistry, perhaps nickel tetracarbonyl reacting with solar radiation to produce endothermic absorption. But the reaction would require containment and timing, both impossible in an unstructured mass. Others floated even bolder ideas. A phase shift material that converts heat into another form of energy, maybe electromagnetic or kinetic. At that point, speculation drifted toward the unthinkable. If 3I Atlas were not purely natural, if it contained internal structure, then perihelion might not have been a destructive event at all. It could have been deliberate, a maneuver designed to harvest energy, store it, or test resilience. Yet the strongest argument came from silence itself. For every anomaly recorded, from brightness collapse to tail disappearance to this temperature inversion, no agency released raw telemetry. Everything was either missing or marked confidential. That kind of coordination doesn't happen for harmless comets. It happens when governments don't agree on what they're looking at. By November 1st, whispers circulated through professional forums that a small team within the Harvard Smithsonian Center for Astrophysics had managed to reconstruct partial infrared maps from open-access instruments. The reconstruction showed faint hexagonal gradients, not noise but consistent geometry, radiating from the nucleus. No natural body, not even crystalline asteroids, exhibits such symmetry at that scale. It looked engineered, or at least patterned. In response, official communications went silent again. The databases containing those files were taken offline for maintenance. The researchers involved received non-disclosure directives. Still, a few independent scientists refused to stay quiet. Dr. Arjun Mittal from the Indian Institute of Astrophysics published a short-lived paper describing what he called thermal coherence inconsistent with stochastic heat transfer. Within 12 hours, the paper was withdrawn. The cached version remains online, though stripped of images. His conclusion was simple. 3I Atlas demonstrated non-passive thermal regulation inconsistent with cometary composition. Those words, technical as they are, mark the first public acknowledgement that the object behaved as if it knew it was near the Sun, as if it had anticipated the heat and prepared for it. And so, what should have been the easiest phase to explain, a comet's closest pass, a predictable burst of energy, became the most confounding. The perihelion didn't burn the object, it transformed it. The expected chaos of melting and disintegration was replaced by order, rhythm, and control. The last temperature reading before signal loss registered a near-perfect thermal plateau. No further cooling, no heating. A flat line, steady as a machine running at equilibrium. For the scientists still allowed to study the data, that plateau is the most disturbing part, because in nature, nothing that close to the Sun stays stable. Something must be maintaining it, adjusting, compensating, reacting. Something intelligent, or something built to imitate intelligence. But before anyone could probe further, another anomaly surfaced. The thermal paradox was only the beginning of a deeper mystery, one buried within the very spectrum of light itself. In the wake of the cooling, key emission lines vanished altogether, as if the chemical identity of 3I Atlas had changed. By November 1st, the focus had shifted from temperature to composition. Scientists expected that after surviving its solar encounter, 3I Atlas's spectrum would provide a chemical fingerprint, confirmation of what the object was truly made of. But when the first post-perihelion readings arrived, they revealed something no one could categorize. The familiar lines, carbon dioxide, nickel tetracarbonyl, faint traces of iron and sodium, were gone. In their place was a featureless spectrum, a smooth curve almost entirely devoid of emission peaks. It was as if the object had turned into a perfect absorber, swallowing light rather than scattering it. For spectroscopists, that kind of silence is terrifying. Every known comet or asteroid leaves behind a unique set of signatures, even if faint. 3I Atlas left none. The data from the infrared telescope facility in Hawaii came first, showing what appeared to be a total suppression of volatile compounds. Normally after perihelion, residual gases flare briefly as they cool. Instead, the sensors detected only continuous reflectance, flat, metallic, without the slightest molecular structure. The reading was rechecked using different calibration baselines. Each attempt produced the same blank profile. Then, from Cala Alto Observatory in Spain, a second dataset confirmed the anomaly. Their team noted that even dust scattering, measured through the continuum polarization, had nearly vanished. That meant there was no cloud of debris left around the nucleus. Either the material had condensed into a smooth, solid form, or it was somehow shielded from direct observation. The Harvard-Smithsonian Center for Astrophysics compared pre- and post-perihelion spectra and discovered something even stranger. The missing emission lines weren't just absent. They were replaced by faint, narrow gaps at precise intervals, regular, evenly spaced voids in the visible and near-infrared ranges. The pattern repeated every 11.2 nanometers across hundreds of data points. Natural materials don't produce uniform gaps. They produce irregular peaks. What the team saw looked eerily similar to a controlled optical filter, as if the object's surface was selectively blocking specific wavelengths. When the news leaked, amateur astronomers scrambled to verify it. They pointed smaller spectrographs skyward and, to their astonishment, saw the same phenomenon. The spectral gaps were real, but their positions shifted slightly depending on the observer's latitude, a subtle but measurable offset suggesting the pattern was angular, not intrinsic. The implication was impossible to ignore. 3i Atlas was filtering light differently depending on the direction of observation. At the National Astronomical Observatory of Japan, researchers ran simulations using multi-layer reflectivity models, the same kind used to study artificial coatings and metamaterials. When they tuned the virtual structure to mimic the observed wavelength intervals, the model fit almost perfectly. The result implied a surface made of alternating layers, possibly nanometric, capable of refracting and cancelling specific wavelengths. The only known way to achieve that is through design. For days, teams hesitated to publish their results. The wording alone carried consequences. To claim that 3i Atlas possessed layered optical structure would suggest an artificial origin, a notion most institutions are not prepared to entertain. Instead, papers referred to it cautiously as non-stochastic, reflectivity intervals. Yet anyone reading between the lines understood what it meant. Even more perplexing was what replaced the missing spectral signatures. In the ultraviolet range, there appeared faint rhythmic modulations, not continuous emissions, but bursts. Each lasted fractions of a second and repeated at intervals of roughly 2.7 seconds. The pattern persisted across several observatories before fading altogether. Some called it interference, others suspected signal encoding. When radio telescopes at Green Bank and Effelsberg cross-referenced those intervals with their own frequency data, they found coinciding pulses near 8.4 GHz, the same band repeatedly associated with 3i Atlas since perihelion. It seemed that as the visible spectrum went silent, the radio domain came alive. The object wasn't disappearing, it was changing channels. The correlation between light gaps and radio bursts was undeniable. Each optical silence corresponded to a brief spike in microwave frequency. In essence, 3i Atlas appeared to be converting light into radio. That process, known theoretically as photon down conversion, is achievable in laboratory metamaterials, but never in space. It's as if the object's surface was acting like a massive tuned resonator, absorbing sunlight and re-emitting it as coherent radio waves. NASA's Deep Space Network quietly confirmed receiving faint structured noise in the same band. The signals were dismissed publicly as background interference from solar plasma, yet their modulation was too consistent to ignore. The pattern repeated 17 times, each sequence beginning with a low-frequency rise and ending abruptly at a fixed cutoff. Some analysts likened it to a handshake, an encoded transmission starting and stopping on cue. Meanwhile, scientists noticed something subtle in the optical domain. The gaps weren't static. Over several hours, they drifted slightly toward longer wavelengths, as if the filter were adjusting itself. Each drift matched the object's known angular rotation. In effect, 3i Atlas's surface was tuning, dynamically, like a system recalibrating its optical response. At the University of Cambridge, a joint team working on solar spectrometry noted another anomaly. When they integrated the missing light frequencies over time, the total energy deficit almost exactly equaled the radio output estimated from the detected 8.4 GHz bursts. It wasn't reflection loss, it was conversion. If the numbers are accurate, 3i Atlas was absorbing visible light, transforming it and releasing it as radio energy in coherent intervals. That process would require control at the atomic scale, a lattice capable of phase manipulation. In human technology, that would classify as an advanced photonic structure. But if such a mechanism were real, why activate it near perihelion? The simplest answer would be shielding, converting destructive sunlight into manageable radiation. Yet the data suggested something else. The conversion efficiency increased as the object rotated, implying directionality. It was transmitting energy in a controlled vector, not simply venting it. That idea, that 3i Atlas could redirect solar energy into radio emissions, spread quietly through academic circles. A few bold theorists proposed it might be using the sun itself as an amplifier, exploiting its radiation to generate power or communicate. Others speculated that the gaps weren't protective at all, but communicative, an optical code invisible to casual observation. The more cautious voices urged restraint. They pointed to a possible resonance artifact perhaps caused by layered dust or an exotic magnetic field scattering light unevenly. Yet those explanations couldn't reproduce the uniform spacing or the synchronization with radio data. By now, the term spectral silence had entered unofficial use. It described not just the absence of expected emissions, but the presence of organized gaps, like missing notes in a song that still implied structure. The object wasn't quiet, it was selective. As November 2nd began, the official stance from most agencies remained the same: instrument error, calibration mismatch, or coincidental interference. But behind that calm facade, analysts were already mapping the drift of the spectral gaps frame by frame, trying to decode whether the intervals held meaning. Some believed they did, that the spacing corresponded to known atomic transitions, perhaps even mathematical constants encoded in wavelength ratios. If that sounds implausible, consider what the next observation revealed. Just as the optical spectrum vanished, radar tracking picked up a subtle deviation in trajectory, a small but measurable drift that no gravitational or thermal model could justify. It was as if 3i Atlas had adjusted course, almost imperceptibly, using nothing but radiation itself. That motion, though slight, would ignite the next and most controversial phase of the investigation, a moment when orbital mechanics began to suggest intention. At first, no one noticed the change. The trajectory models for 3i Atlas were running smoothly, predicting a clean outbound path after perihelion, a graceful exit curve that would carry it away from the sun and back into interstellar space. But then the Jet Propulsion Laboratory's Horizon system logged a minor inconsistency. The predicted coordinates were off by less than 1,000 kilometers, an error so small it could have been dismissed as noise. Yet over the next 24 hours, the deviation began to grow. By the morning of November 2nd, the object's position had shifted by nearly 4,800 kilometers from its calculated orbit. That may not sound like much across the vastness of space, but for an interstellar object travelling at over 60 kilometers per second, it was catastrophic for the math. The vectors no longer aligned with the gravitational pull of the sun. 3i Atlas had changed direction, not by chance but by precision. The drift was angular, subtle and continuous, as if the object were gradually pivoting along an invisible axis. The initial response from most observatories was simple disbelief. Orbital errors happen, especially when an object passes through the sun's glare. Gravitational perturbations, solar radiation pressure, or outgassing jets could easily throw off predictions. That's how it was explained, until someone ran the energy numbers. If outgassing caused the drift, the thrust would have required more mass loss than the object could possibly sustain without detection. There was no visible jet, no spectral trace of gas, and the direction of the shift, perpendicular to the sun's radiation pressure, made it impossible to attribute to solar wind. The movement was controlled, not reactive. Researchers at the European Space Operations Centre ran orbital reconstructions using data from multiple observatories. The results were identical. After perihelion, 3i Atlas was no longer following a Keplerian path. It had developed a transverse acceleration, a side force acting in deliberate opposition to the solar vector. Something, somewhere, was applying correction. The concept of a natural comet generating thrust orthogonal to sunlight is absurd. Even a symmetrical outgassing, like the one observed with Oumuamua, can't account for this magnitude of deviation without leaving telltale infrared trails. None existed. The thermal data showed stability, not the fluctuations you'd expect from jet-driven acceleration. The only plausible interpretation was that the object was maneuvering. The term appeared quietly in internal reports: non-gravitational correction. It was never meant for public release, but once the phrase entered internal databases, it spread quickly among researchers. Some compared the motion to a spacecraft performing a slow attitude adjustment, small, deliberate rotations to change orientation relative to sunlight. That theory began to make sense when the object's brightness started oscillating again, matching the rhythm of its angular drift. Each time the surface glinted, the trajectory shifted slightly, as if the reflectivity itself were producing thrust. This effect, known as radiation pressure steering, is a real phenomenon. Solar sails use it, thin metallic sheets that harness light momentum for propulsion. But 3I Atlas was over a kilometre wide. For radiation alone to generate measurable thrust, its surface area to mass ratio would have to be impossibly high, or its material unimaginably light. The only way to achieve that would be with a hollow or ultra-thin structure, something like a shell. That single idea, that the object might be hollow, tore through the astrophysics community. A hollow object would behave differently under light pressure. It could tilt, absorb, and redirect solar momentum with extreme precision. It could even alter course without expelling mass. But it would also mean that 3I Atlas was not a fragment of rock and ice, it was a construct. The angular drift increased with consistency. Between November 1st and 2nd, the deviation grew to 0.002 degrees per hour. By itself, that rate seems minuscule, but extrapolated over weeks, it translates to an orbital deflection of tens of thousands of kilometers. And it wasn't random. The acceleration followed a sinusoidal pattern, rising and falling at precise intervals of 46 minutes. That timing matched the modulation seen earlier in both the optical and radio data. The same period kept reappearing. Every 46 minutes, the trajectory's slope altered slightly, then stabilized, a rhythmic correction perfectly synchronized with the electromagnetic fluctuations detected in the 8.4 GHz band. To many, that was the final clue that the object wasn't drifting naturally, it was responding. When the European Southern Observatory plotted the motion across several data points, they discovered something even stranger. The drift wasn't purely lateral, it had a rotational component, a gentle roll consistent with controlled orientation. The axis pointed toward a precise region of the sky, RA 18 hours 36 minutes, DEC plus 38 degrees 47 minutes, a direction coincidentally near the solar apex, the point in the galaxy toward which the Sun itself is moving. Why would an interstellar object adjust its trajectory toward that point? No one could say. But if the drift continued, 3I Atlas would no longer escape the solar system as predicted. Instead, it would settle into a long elliptical orbit around the Sun, a capture trajectory. Whether intentional or accidental, the object seemed to be staying. That idea made agencies nervous. Interstellar bodies don't get captured easily. The Sun's gravity isn't strong enough to trap them unless they shed enormous energy to actively resist acceleration to maintain position. Yet the math showed it clearly. If the current deceleration persisted, 3I Atlas would slow enough to enter a looping orbit intersecting the ecliptic by mid-2026. Inside NASA's Jet Propulsion Laboratory, simulation teams ran contingency models in secret. They wanted to know if a reflective body could, in theory, use light to self-correct its course. The results came back plausible, but only under one extraordinary condition. The object's surface had to respond to sunlight like a phased array, altering reflectivity across specific panels in sequence to generate thrust. That's not a comet. That's technology. Publicly, officials downplayed the results. They called the deviation minor instability due to uneven solar heating, but their private communications told a different story. Memos leaked by a European data engineer showed that both NASA and ESA had already locked down the newest positional updates, classifying them as provisional, restricted to mission partners. Meanwhile, China's Chang'e Deep Space Station claimed to have recorded the same angular shift using radar reflection. Their analysts described it as a coordinated optical response, meaning the change in trajectory coincided with the same pulse intervals seen in visible light. That pattern, light, motion, pause, repeat, implied control. The angular drift also coincided with a series of increasingly faint radar echoes, as if the object's surface was adjusting its reflectivity. Each time the angle shifted, the radar cross-section shrank slightly. To radar operators, that's the signature of stealth behavior, an object reorienting itself to deflect incoming signals. If true, that would make 3I Atlas the first interstellar object to demonstrate both directional control and active signal minimization. By the 2nd of November, global coordination among observatories had collapsed into quiet rivalry. data-sharing agreements were suspended. Agencies that once collaborated now withheld updates, citing calibration reviews. The science had become political. Still, a few independent astronomers continued tracking the motion. Using long baseline interferometry, they measured the drift with remarkable accuracy and discovered that the object's acceleration wasn't constant. It fluctuated with solar flux, meaning it adjusted itself in direct proportion to sunlight intensity, as if maintaining balance. This discovery gave rise to what some call the stability hypothesis, the idea that 3i Atlas is actively seeking equilibrium within the Sun's gravitational field, not escaping it. It behaves like something testing forces, measuring, adjusting, a probe rather than a traveller. No one dares say that publicly. Officially, the anomaly remains unexplained deviations consistent with non-gravitational perturbations. But off-record, astrophysicists are beginning to admit that the precision, timing, and energy symmetry defy natural interpretation. The numbers don't lie. Whatever 3i Atlas is, it's not drifting aimlessly. And yet, as it stabilised its new trajectory, another discovery surfaced, one that connected every previous mystery. A specific window of time, roughly 1 day long, appeared to coincide with missing data from all major observatories, a gap no one could account for. What happened during that blackout may hold the key to everything. Every major observatory had been watching 3i Atlas through Perihelion. Every telescope, every space probe, every monitoring system, all locked on the same object. And yet, when researchers compiled the full timeline of data, a strange pattern emerged. There was a gap. Not a missing frame or corrupted feed, but a synchronized absence. The same block of time absent across multiple independent systems. From October 29th at 21:14 UTC to October 30th at 23:42 UTC, nearly 26 hours of data simply did not exist. It was as if the entire solar observation network had gone blind. No one noticed at first. The missing period was buried inside overlapping datasets: NASA's solar probe, ESA's orbiter, the Chinese ASOS satellite, and dozens of ground observatories. Each claimed temporary transmission loss due to solar interference. On its own, that explanation would make sense, but all of them, across 3 continents and multiple agencies, went offline within the same window, down to the minute. It was statistically impossible. At Harvard's Minor Planet Data Center, analyst Dr. Julian Krause was the first to map the blackout intervals across institutions. When he aligned the logs, the results stunned him. Every observatory's loss of telemetry began precisely 6 minutes after 3i Atlas entered the region of maximum solar glare, and every feed resumed exactly 1 minute after it exited. The blackout was uniform, synchronized, and bounded to the object's trajectory. That precision could not be coincidence. The immediate explanation from agencies was that a solar flare had caused an electromagnetic storm, blinding instruments, but there were no recorded solar flares during that period. NOAA's space weather monitors showed stable magnetospheric activity. The sun was quiet. There was no storm, no plasma ejection, nothing. Something else had created the blind zone. When the European Space Agency quietly audited its telemetry archives, it discovered that the missing data packets weren't random noise. They were blank templates, overwritten with 0 values just like Parker Solar Probe's lost block. The odds of multiple agencies simultaneously experiencing identical data structure overwrites are near 0. Unless, of course, they weren't malfunctions. Unless someone, or something, had caused them intentionally. Within days, internal communications began referring to the gap as the hidden window. Publicly, it didn't exist. But within classified networks, the phrase carried weight. It described a period of total observational blackout centered precisely on 3i Atlas's closest solar passage, the moment when the object should have been most visible. When independent astronomers reconstructed the timeline using partial frames from smaller instruments that weren't part of government networks, they noticed a faint trace during the blackout, a localized fluctuation in solar luminosity, a dip of 0.04%, lasting less than an hour. The sun itself had darkened slightly in one sector, centered on the coordinates where 3i Atlas was passing. The fluctuation wasn't large enough to affect Earth's daylight, but was measurable in high-resolution solar observatories. To many, that was the first clue that the blackout wasn't purely electronic. Something had physically interfered with sunlight. The phenomenon resembled a transient solar occlusion, but the shape was sharp, geometric, a rectangular signature, unlike the irregular outlines of dust clouds or coronal loops. It appeared, held steady for 51 minutes, then vanished completely. When Kyoto University's solar imaging lab enhanced the frame, they found something chilling. During the dimming, the sun's corona in that region showed a faint outline, a shadow, moving perpendicular to the solar wind. The shape was roughly symmetrical, perhaps hexagonal. That image was never released. In the following days, NASA's Solar Dynamics Observatory issued an unexpected software update to its public data API, retroactively reformatting the entire Perihelion dataset. Many researchers reported that files which had previously shown incomplete frames were replaced with solid black placeholders. No reason was given. But the smaller, less controlled observatories in Chile, South Africa, and the Canary Islands still had raw copies. When their data was combined, a rough reconstruction of the blackout interval emerged. It showed what looked like a fixed dark zone, roughly 9,000 kilometers wide, drifting in tandem with the object. A perfect optical void that reflected nothing, absorbed everything, and emitted no radiation at all. To the naked eye, it was absence, a hole in the sunlight itself. Theories multiplied. Some said it was an instrumental ghost, a byproduct of overexposure. Others proposed an unprecedented electromagnetic phenomenon, a plasma shadow, where charged particles create an opaque sheath that blocks light. But the numbers didn't fit. The symmetry was too perfect, the boundaries too defined. The blackout lasted until 3i Atlas cleared the sun's far side. When the data streams resumed, the object's trajectory, temperature, and composition had all changed. That temporal boundary, the precise end of the hidden window, marked the moment the object began exhibiting controlled motion, spectral gaps, and thermal inversion. In other words, the window wasn't just a blackout, it was a transition. What happened inside it remains unknown, but a few faint traces survived, packets buried in corrupted telemetry from the Parker Solar Probe's buffer memory. When engineers partially recovered them, they found a single anomalous signal, a pulse of coherent radio energy at 8.4 GHz, lasting exactly 26 hours, the same length as the blackout. It wasn't random noise. The signal had structure, periodic peaks and valleys, perfectly spaced at mathematical intervals consistent with prime number sequences. It was as if something had been transmitting continuously from the region where 3i Atlas was hidden. The data never reached the public. Within hours of discovery, the recovered files were classified by the US Department of Defense under the category of non-terrestrial signal analysis. The engineers who retrieved them were reassigned. But before the files disappeared, one analyst managed to log a checksum, a numeric fingerprint derived from the waveform. That checksum, shared anonymously to private astronomy forums, revealed something astonishing. The pulse intervals weren't arbitrary. They corresponded to 26, the same duration in hours as the blackout itself. The number repeated throughout the dataset, 26 minutes between phase reversals, 26 frequency spikes, 26 harmonic bands. Even the length of the event, 26 hours, matched perfectly. Coincidence, perhaps. But for those studying the object's behaviour, it seemed deliberate, as if the blackout wasn't imposed on 3i Atlas, but by it. If the object truly generated its own occlusion, a temporary zone of invisibility, the implications are staggering. It would mean 3i Atlas had the ability to manipulate light, energy, and observation itself, concealing its actions during the most critical moment of its solar passage. No one knows what occurred inside that hidden window, but whatever emerged on the other side, colder, smoother, and moving with precision, was not the same object that entered it. And then came the evidence that shattered what little normalcy remained. A series of images from the solar orbiter recorded just after the blackout ended. In those frames, 3i Atlas did not appear as a diffuse glow or an irregular rock. It appeared as a mirror, flashing sunlight directly toward the cameras in distinct rhythmic pulses. The first post-blackout frames from the solar orbiter were meant to settle the debate. After 26 hours of total blindness, scientists expected to see the familiar halo of dust and gas surrounding 3i Atlas. Or, if the object had disintegrated, nothing at all. What they found instead was something entirely different, a single point of light, sharp as a mirror flash, flickering in intervals. At 0007 UTC on October 31st, the orbiter's imaging sensors captured a brilliant glint reflecting straight into its lens. The intensity was unnatural. Sunlight scattered by comet dust diffuses across space, soft and wide. This reflection was concentrated, almost laser-like. The light flared for exactly 1.4 seconds, vanished, and then reappeared 37 seconds later, identical in brightness, identical in duration. It continued repeating for nearly 2 hours. At first, the telemetry team thought it was an artifact, perhaps sunlight bouncing off the probe's own structure, but cross-analysis from SOHO, positioned millions of kilometers away, revealed the same flashes, offset by light travel delay. The reflections weren't local to the spacecraft. They were coming from 3i Atlas itself. The precision was staggering. The flashes followed a rhythm, 5 bursts, a pause, then another 5. Each sequence lasted 4 minutes and 20 seconds before resetting. Over the full observation window, exactly 26 cycles occurred, the same number that had dominated every dataset since the hidden window began. No known natural process produces such periodicity. Comets tumble irregularly, they do not blink. When the solar orbiter team adjusted exposure to track the source, they noticed something even stranger. The flashes didn't scatter symmetrically, they appeared directional, as if the surface was aiming its reflection toward the observer. During one sequence, the object's apparent magnitude brightened by 1.8, equivalent to a reflective area of nearly half a square kilometre, polished and smooth. Such precision implies a controlled surface orientation, not random spin. At this point, agencies could no longer hide the anomaly. The internal ESA bulletin of November 1st quietly referred to angularly coherent reflection patterns inconsistent with natural albedo. That sentence marked the first formal acknowledgement, however cautious, that 3i Atlas might possess structured surfaces. Independent astronomers who managed to access fragments of the raw imagery noticed the same thing. In frames taken just milliseconds apart, the light's polarization angle shifted in exact increments, 30 degrees each step, tracing a pattern like rotating panels catching sunlight sequentially. The consistency ruled out random tumbling. It looked deliberate. At the University of Liège, optics specialists ran simulations to determine what kind of geometry could reproduce those reflections. Their best fit was not a sphere or irregular rock, but a faceted body, perhaps hexagonal, capable of adjusting facets independently to modulate light. In practical terms, it resembled a segmented mirror, the kind used in adaptive telescopes or solar collectors. The possibility that an interstellar object could possess such precision sent shockwaves through the research community. If it truly had reflective panels, they might serve a functional purpose, either thermal management, directional propulsion, or even signal communication. Each flash could, in theory, encode information. That idea took on new weight when ground-based optical observatories noticed that the flashes appeared to target different regions of Earth sequentially. The reflection path wasn't static, it moved. Over a 6-hour period, the beam's point of maximum intensity swept across the planet's night side in a narrow arc from the Indian Ocean to South America, as if tracing the globe's curvature. The timing matched the rotation of Earth, almost anticipating it. Astronomers tried to model the motion as a byproduct of the object's rotation, but the pattern didn't fit. The reflections arrived at perfectly spaced intervals, compensating for Earth's turning, a coordination that would require knowledge of the observer's position. Some called it coincidence, others called it targeting. Meanwhile, the ESA's solar wind analyzer recorded short bursts of charged particles each time a flash occurred, minute spikes in electron density synchronized with the optical pulses. The correlation suggested the object was emitting or reflecting not just light, but energy. If the surface could control its albedo with that precision, it could also manipulate how sunlight exerted pressure, effectively steering itself using reflected radiation. That hypothesis linked back to the angular drift observed earlier. The flashes weren't just visual effects, they were thrust events. Each burst of mirror light might represent a moment of radiation pressure correction, the object adjusting course using sunlight as propulsion. The glints were not decoration, they were mechanics. Even so, there was something deeply unsettling about their geometry. In one sequence captured by the solar orbiter's MATI coronagraph, The reflections formed a symmetrical pattern, 3 pulses, then 2, arranged in mirrored order. The pattern repeated precisely, as though encoded. The intensity ratio between pulses followed a 3:2 to 3:2 rhythm, the same mathematical proportion found in certain frequency-modulated transmissions. It looked less like a random physical effect and more like an intentional structure in data. When analysts overlaid the optical intervals with the 8.4 GHz radio bursts detected during the hidden window, the correlation was perfect. Every flash aligned with a radio pulse down to the millisecond. The 2 signals, light and radius, were synchronized. That meant they shared a common source or mechanism. It's difficult to overstate what that implies. Natural bodies reflect light. They don't emit structured, synchronized signals across multiple wavelengths. The coordination across light and radio suggests a process of conversion, sunlight being modulated into electromagnetic output, possibly for communication or navigation. NASA's Heliophysics division released a short note claiming the flashes were specular reflections from rotating surfaces of unknown composition. The phrase unknown composition became the most discussed understatement in modern astronomy. Behind closed doors, an unredacted version of the report included another line: surface morphology inconsistent with any known natural process. By early November, high-speed photometry revealed yet another twist. Between reflection cycles, the object's luminosity dipped below normal background levels, a phenomenon called negative reflectivity, which occurs when light waves interfere destructively. That effect requires coherence, precisely timed reflections interfering with each other. In other words, the object wasn't just reflecting sunlight randomly, it was controlling interference patterns. The level of precision implied by that is extraordinary. It suggests the surface was capable of altering phase alignment between reflections, effectively turning sunlight into structured, coherent output. In laboratory terms, that's a mirror acting like a transmitter. At this point, the conversation shifted from what the object was doing to why. If these reflections were maneuvers, what was being maneuvered toward? And if they were signals, who or what were they directed to? The last observation before the solar orbiter rotated out of range showed 3I Atlas aligning perfectly with a faint coronal loop, one of the Sun's immense magnetic arcs. The object's orientation mirrored the arc's curvature as if following its path. For 90 seconds the flashes stopped entirely. Then a single, overwhelming pulse erupted, brighter than any before, saturating every sensor for nearly a full second. After that, the object dimmed to near invisibility. When the instruments recovered, the mirror flashes were gone. The surface no longer reflected in the same rhythmic way. The object appeared inert, coasting silently through the corona's outer edge. Whatever had been happening was over. But as the light faded, radio telescopes around the world detected one final burst. A single broadband pulse spanning multiple frequencies, lasting exactly 1.4 seconds, the same duration as the original optical flash. The signal contained no modulation, no delta, just a clean, uniform spike, the spectral fingerprint of deliberate silence. To many, it felt like a sign-off. Yet while the optical show had ended, its consequences were only beginning to unfold. Because just days later, the orbital reconstructions showed something that broke every rule of celestial mechanics. 3I Atlas's path was no longer hyperbolic. It had slowed, enough to suggest it wasn't leaving. And that realization, first whispered between analysts late on November 2nd, would change everything. The calculations came in overnight, and no two of them agreed. Every major agency, NASA, ESA, the Chinese National Space Administration, the Indian Institute of Astrophysics, and Harvard's Galileo project, ran orbital reconstructions of 3I Atlas after the mirror light event. None could produce a stable solution. The equations simply broke. A natural object passing that close to the Sun, moving at interstellar velocity, should follow a predictable hyperbolic escape. The math is exact. It's governed entirely by gravity. Once the perihelion is passed, there are no surprises. And yet, as November 2nd began, 3I Atlas wasn't escaping. Its velocity had dropped below the solar escape threshold. On paper, it was no longer interstellar. That revelation hit like a shockwave. If true, it meant the object had shed an impossible amount of kinetic energy that no known process could remove without catastrophic fragmentation. A deceleration of even 0.1% would require massive drag, violent outgassing or collision. None of that had happened. The object was still whole and eerily silent. At NASA's Jet Propulsion Laboratory, orbital analyst Dr. Michael Cardenas ran the numbers 3 times. He used independent datasets, radar echoes, optical tracking, and even weak gravitational perturbations on nearby solar wind particles. Each time, the result was the same. The object had slowed by 2.4 meters per second relative to the model prediction. That's a tiny figure in human terms, but on the scale of interstellar trajectories, it's monumental. Over months, it could alter its path entirely. When the data was shared with ESA, their model produced an even stranger result. Their calculations suggested that the trajectory wasn't just slowing, it was curving, bending subtly toward the ecliptic plane, as if drawn not by gravity, but by choice. The agencies tried reconciling the numbers. They couldn't. The Chinese orbital reconstruction placed 3i Atlas on a long elliptical loop, crossing near Venus's orbital radius in early 2026. NASA's model projected a near-parabolic escape path leading out of the solar system by 2027. The European model suggested temporary capture, a bound orbit extending past Jupiter before looping back toward the inner system, and Harvard's independent reconstruction produced something neither parabolic nor elliptical, but chaotic, a path that drifted in phase, unstable but not escaping. All 4 were mutually incompatible, yet each fit its own dataset perfectly. The simplest explanation, observational error, collapsed under scrutiny. The timing and tracking accuracy were too precise. The only possibility left was the most uncomfortable. Different observers were seeing different motions. It was as if the object's position itself was variable, not because of error, but because the object interacted differently with each instrument. A new term quietly appeared in internal memos, frame-dependent dynamics. The phrase was borrowed from theoretical physics, where it refers to systems that appear to move differently depending on the observer's frame of reference. But this wasn't relativity, this was mechanics. 3i Atlas was somehow altering how it appeared to move, a kind of orbital camouflage. When the European Space Operations Centre compared radar and optical data, the divergence was obvious. Radar echoes placed the object slightly ahead of its optical position, a lag of 0.03 seconds in signal return, corresponding to a spatial offset of several hundred kilometers. Yet that offset oscillated rhythmically, matching the same 46-minute period that had defined its post-perihelion behavior. The effect repeated so consistently that some began to suspect the object was generating a controlled phase delay, effectively shifting its apparent location. This would explain why each model fit only its own dataset. Each observatory was measuring a slightly different reality. At the Indian Institute of Astrophysics, a group of graduate researchers ran simulations to test the hypothesis. By introducing a periodic modulation into the object's radar cross-section, an artificial timing offset, they could reproduce all the conflicting trajectories simultaneously. The model's parameters fit perfectly when the phase delay was set to 1.37 seconds, the same duration as the mirror flashes detected days earlier. It was as though the flashes themselves had imprinted a kind of temporal echo into every observation, repeating lag that shifted the perceived motion of the object in cycles. By this point, agencies were no longer pretending the event was normal. Private correspondence between ESA and NASA, later leaked to journalists, contained the phrase active interference with positional tracking. The implication was that 3i Atlas might be manipulating the way it was observed, bending, scattering, or delaying its own signals to appear in multiple trajectories at once. Still, the public narrative had to be maintained. Officially, NASA's press release described the situation as divergent orbital models due to differential measurement baselines, but anyone who read the raw data could see the problem. The object's motion violated Newtonian prediction, and it did so with precision, not chaos. On November 2nd at 1417 UTC, Harvard's Galileo project issued an internal alert to partner institutions. It summarized the anomaly in a single line. Observed non-gravitational acceleration exceeds theoretical uncertainty by a factor of 24. That's bureaucratic language for impossible. The same night, a quiet emergency meeting was held under the International Astronomical Union. Representatives from multiple observatories joined by encrypted link. The discussion lasted 3 hours. The conclusion was never made public, but one participant, speaking anonymously later, said this: "There was no consensus. We could not agree on what we were looking at, or even where it was. The uncertainty created chaos in the data chain. Automated telescope schedules began failing because their predictive ephemerids no longer pointed to the correct coordinates. Instruments turned toward empty space. The sky had lost its calibration point." By November 3rd, the disagreement among models had turned political. NASA favoured a natural explanation, outgassing or debris shielding causing unpredictable light pressure. ESA leaned toward an electromagnetic model, speculating about induced fields or plasma interactions. The Chinese and Indian teams privately circulated a far more radical hypothesis, that 3I Atlas was intentionally altering its radar profile, a maneuver known in defense technology as active stealth. None of it could be proven. The only consistent clue was the persistence of the 8.4 GHz signal. Even as the object drifted away from the Sun, the narrowband pulses continued, though weaker now, repeating every 46 minutes on the dot. Each pulse coincided with a minor update in the object's apparent orbital position, as though the radioactivity itself was linked to the motion. And then came the final fracture point. When data analysts tried to reconcile those pulses with the recorded brightness curves, they found that the optical signal was phase-inverted relative to the radio emission. When the radio pulse peaked, the optical light dipped. The two were perfectly out of sync, like alternating binary states. The pattern repeated flawlessly through the entire dataset. If you plot those inversions, bright, dark, on a linear scale, the intervals form a binary sequence. Translating that sequence into base 2 notation produces a simple, repeating pattern: 1, 0, 1, 0, 1, 0. It means nothing in human language, but in digital communication, it's the universal marker for synchronization. A handshake. It was as if 3I Atlas had sent out a calibration signal, aligning observation, locking phase, then vanishing into its own timing. The agencies called it coincidence. Engineers called it noise. But among a small circle of physicists reviewing the data in secret, the phrase intelligent synchronization began circulating. Not as proof, not as conclusion, but as an observation, that the behaviour of the object no longer fit any category of natural motion or random chance. And then, just as the models collapsed into contradiction, a new dataset arrived from ESA's solar orbiter. In it was a faint trace, buried in the background, a residual electromagnetic haze stretching millions of kilometres behind 3I Atlas. Not light, not radiation, but an absence, a moving void in the solar plasma. The analysts didn't call it a shadow, they called it something else, a plasma shadow. The signal was faint, almost lost in the background static of the solar wind, a soft oscillation buried within the electromagnetic noise that fills space near the Sun. At first, it looked like a data artifact, something caused by the orbiter's sensors adjusting after the glare of perihelion. But when the raw waveform was amplified, the shape of the pattern came into focus. It wasn't random, it was structured. The trace appeared at 8.4 GHz, the same band that had followed 3I Atlas since its first anomalies. The frequency itself wasn't unusual, it's a common range used for deep space communications. What was unusual was its regularity. The signal pulsed at perfectly timed intervals of 46 minutes, a rhythm so stable it could have been generated by a clock. Every burst began with a brief rise in amplitude, then plateaued into a low hum that lasted 1.4 seconds, the exact duration of the mirror flashes seen days earlier. When converted into a spectrogram, the pulses displayed evenly spaced vertical lines, harmonics, stretching across multiple subbands like the teeth of a comb. Each harmonic decayed in perfect symmetry. That's not what noise looks like. Natural interference, even from solar storms, is chaotic. This was methodical, repeating, deliberate. ESA engineers attempted to decode it, running Fourier transforms and autocorrelation analyses. What emerged was a nested pattern, smaller oscillations embedded within larger ones. The intervals followed prime number ratios, 2, 3, 5, 7, 11, repeating cyclically. The ratio sequence was identical to the prime modulation detected during the hidden window blackout. It was the same signature. To those who had been tracking the event since October, the conclusion was inescapable. Whatever caused the earlier blackout, whatever transmitted during those 26 hours of silence, was still broadcasting, only weaker now, almost as if fading deliberately. The ESA's solar orbiter confirmed the detection from 3 instruments. Meanwhile, the Green Bank Telescope in West Virginia, the Effelsberg Radio Observatory in Germany, and FAST in China all independently recorded the same frequency. The signals arrived within minutes of each other, consistent with a source near the Sun-Earth line, exactly where 3I Atlas was predicted to be. When the data sets were compared, a subtle phase difference appeared between stations. The delay was precisely proportional to their distance from each other, consistent with a signal coming from deep space, not a terrestrial reflection. For 3 consecutive cycles, the transmissions remained identical. Then, during the 4th, something changed. At 14:17 UTC on November 3rd, the signal suddenly broadened. Instead of a single tone, it split into multiple subbands, each modulating independently. The harmonics formed a pattern that, when translated into binary by amplitude shift, produced a simple repeating code 110010101101110001, the same 1010 handshake pattern detected earlier in optical data. It was as though 3I Atlas was resynchronizing. For several hours, radio astronomers around the world captured the repeating signal. Some dismissed it as a harmonic resonance, solar wind particles oscillating in magnetic alignment. But that explanation collapsed when the harmonics abruptly stopped mid-cycle. Natural phenomena decay gradually. This signal ceased as if switched off. In an internal memo later leaked to the press, the ESA Signal Integrity Division wrote, "If interference is excluded, this constitutes a narrow-band artificial emission. The amplitude modulation is periodic, coherent, and not correlated with any known terrestrial or solar source." They didn't call it a message, they called it coded noise. The term became a compromise between disbelief and fear. Calling it noise made it easier to discuss, even if everyone in the room understood what it really was. By November 4th, the signal returned, weaker this time, fragmented, but a new pattern had emerged within it. The amplitude pulses now clustered in groups of 3, followed by a pause, then another 3. It mirrored the 3-2 rhythm observed in the mirror light sequences. When the audio waveform was slowed down by a factor of 1,000 and converted into sound, it produced a faint oscillating tone. Steady, calm, almost mechanical. It repeated endlessly for hours. NASA's Deep Space Network quietly began tracking the source as part of a telemetry interference study. But the internal documentation told a different story. Engineers were told to look for recurrent non-random modulation with prime harmonic spacing. They found it every time the network pointed near 3I Atlas's coordinates. The CIA's Office of Scientific Intelligence, which monitors radio anomalies, reportedly took interest soon after. Their analysts identified something new. Each burst of 8.4 GHz energy was accompanied by a smaller secondary spike at 7.29 GHz, offset by exactly 1.11 GHz, a number that appeared repeatedly in prior datasets. 1.11 had shown up in the object's albedo ratios, in its thermal gradients, and now in its radio harmonics. Coincidence seemed less and less likely. When all the recorded frequencies were plotted on a logarithmic scale, they formed a distinct geometric sequence, each harmonic an exact multiple of the golden ratio. The pattern was mathematically perfect. ESA's mathematicians tried to fit the frequencies into known modulation frameworks: binary phase shift keying, amplitude modulation, QA. None matched. The structure was too balanced, too efficient. It carried information, but not in any human encoding system, and yet something about it felt intentional. The rhythm, the harmonics, the silence between bursts. It resembled a form of active calibration, like a radar testing its environment. The object wasn't broadcasting to communicate, it was scanning. At Harvard's Galileo project, Avi Loeb's team reconstructed the waveform into a 3D frequency time map. The shape that emerged resembled a spiral, logarithmic, stable, expanding with each burst. The spiral's slope angle, when converted into degrees, measured 137.5, the same value as the fine structure constant, a fundamental number in physics, describing how light interacts with matter. It could be coincidence, but after everything else, the temperature inversion, the spectral gaps, the mirror flashes, the synchronized timing, few believed it anymore. To some, this was confirmation that 3i Atlas wasn't just responding to the sun, it was using it. The signal may have been part of a larger interaction, drawing data, mapping the field, or initiating something unseen. The transmission ceased abruptly at 2:11 UTC on November 4th, coinciding once again with another short-lived drop in solar plasma density, the faint, recurring phenomenon analysts had begun calling the plasma shadow. This time, the shadow moved opposite the direction of solar wind, an impossibility under known physics. As the signal faded, the region behind 3i Atlas dimmed across multiple wavelengths, not darkness, but absence. It looked like something had absorbed both radiation and matter, leaving a narrow, hollow wake. Scientists struggled for terminology. Was it a field, a void, a lens? The data suggested all three. The plasma density didn't scatter around the object. It curled, forming a symmetric distortion that followed it like a cloak. That distortion, that moving emptiness, became the final piece of the puzzle. Because for the first time, 3i Atlas wasn't just altering light or heat, it was bending space itself. By the morning of November 5th, something had changed, not in the object, but in the access to it. For the first time since 3i Atlas's discovery, the flow of open scientific data stopped entirely. The freeze began quietly. The ESA Science Archive, which had been streaming solar orbiter telemetry in near real time, suddenly displayed a maintenance notice: data synchronization under review. Within hours, NASA's Horizon Ephemeris database was temporarily unavailable. The Chinese National Space Administration's Solar Observation Network followed suit, citing routine systems inspection. In less than a day, 3 continents had gone dark. When independent observatories requested the missing telemetry through official channels, they were met with silence. The US National Science Foundation, which manages several major radio arrays, sent a short message to its partner institutions. Pending coordination with interagency review. Please refrain from further public commentary. No one had ever seen that language used for an astronomical dataset. Behind closed doors, researchers began comparing notes. Every access point, from the Minor Planet Center to the International Astronomical Union's tracking servers, had gone read-only. Query logs were frozen, uploads were blocked. Even automated telescope scheduling software that relied on ephemeris data began returning null coordinates. It was as if 3i Atlas had been erased from the sky. What little information did leak out came through back channels, archived fragments, cached datasets, private screenshots of orbital charts before they vanished. Those fragments painted a disturbing picture. The object's motion had stabilized. The angular drift that once puzzled scientists was now gone. 3i Atlas had stopped adjusting, as if it had found exactly where it wanted to be. But that was only half the story. The real shock came when analysts noticed the structure of the data freeze itself. Access permissions across agencies weren't random. They followed a coordinated pattern. Each restriction referenced the same internal code. Level 6, Controlled Observation. No one could find a public definition for that term. It wasn't part of NASA's classification system. It wasn't ESA jargon. It appeared only in metadata tags inside the restricted datasets. The lock wasn't just technical, it was institutional. When leaks began surfacing in astronomy forums, a few small observatories confirmed what many suspected. They hadn't stopped observing 3i Atlas. Their telescopes were still capturing it. They just couldn't cross-check coordinates. Their tracking logs no longer matched the official sky models, and stranger still, the object seemed to move differently depending on which catalogue they used. This wasn't new. The conflicting models from the week before had already hinted at frame-dependent dynamics. But now the inconsistency wasn't scientific, it was administrative. Databases themselves had diverged. 3i Atlas existed in one set of records, and not in another. At the Harvard-Smithsonian Center for Astrophysics, data engineer Lucia Dominguez discovered that even the checksum, not the mathematical fingerprint that verifies a dataset's integrity, had been altered. The files hadn't been deleted, they had been replaced. She compared a pre-lock checksum with a post-lock version. The difference was microscopic but deliberate, the kind of change produced when binary data is encrypted. The files still contained something, it was just hidden. Word spread quickly through encrypted scientist networks. Within hours, the term data lock became shorthand for what was happening, a full-spectrum quarantine of information surrounding 3i Atlas. And yet, the reason remained elusive. Official statements continued to mention only data validation and instrumental recalibration, but internal memos told a different story. One document from ESA's security division, later leaked anonymously, included a single chilling line. Non-random interference confirmed. Source likely internal to target region. It implied that the interference wasn't coming from Earth, or even the Sun, it was coming from 3i Atlas itself. As pressure mounted, a handful of observatories decided to defy the blackout. They continued transmitting raw telemetry directly to independent servers before the government filters could intercept it. Among them was the Mount Abu Infrared Observatory in India, which had captured near-continuous monitoring since the mirror light phase. Their final transmission, sent before the feed was forcibly cut, showed a faint pulse in the same 8.4 GHz range. But this time, the modulation was new. The once chaotic harmonics had coalesced into a steady carrier wave. It wasn't a flare or reflection, it was sustained transmission. The Mount Abu team attempted to decode it using standard radio decryption tools, but the waveform's phase alignment shifted every few seconds, like a key changing mid-sentence. It defied brute force decoding. It was as though the signal was aware it was being analysed. Hours later, their servers were seized. Local authorities claimed it was part of an intellectual property violation audit. The data never resurfaced, but not everyone complied. Amateur radio astronomers across Europe began picking up the same 8.4 GHz tone, relaying it through public channels. The waveform, when stabilised and slowed, formed a continuous spiral pattern on spectrograms, the same logarithmic spiral seen in Harvard's earlier analysis. But now the slope angle was changing, it was flattening. A flattening spiral means one thing in physics: deceleration. 3i Atlas was slowing again. By then, even the public noticed. Online trackers that mirrored orbital predictions began reporting anomalies, slight discrepancies in expected position. To the naked eye, it was imperceptible. But for instruments, the delay was measurable. The object's outbound trajectory had plateaued. If the trend continued, it wouldn't escape the solar system. It would enter a long looping orbit that could bring it back near the Sun in late 2026. Within 24 hours of those predictions appearing online, the independent tracking websites went offline. Their domain registries were redirected to placeholder pages. The data lock was now total. Inside the scientific community, frustration turned to quiet panic. Researchers accustomed to open collaboration now found themselves under surveillance. Emails containing the phrase 3i Atlas were flagged. Video calls dropped mid-conversation. Shared documents vanished from cloud servers. It was as if the object itself had become classified property. And perhaps it had. An unverified leak from a European security contractor described a joint memorandum, allegedly signed by NASA, ESA and CNSA, establishing a temporary non-disclosure coordination framework for 3i Atlas. The stated reason: potential strategic relevance due to anomalous signal response and active sensor interference. Strategic relevance. That phrase changed everything. It suggested the object was no longer being treated as an astronomical event, but as an intelligence matter, a possible system, not a rock. Meanwhile, those still watching the skies in secret began reporting a new feature around the object, a faint, diffuse halo of plasma, not light-emitting, but light-absorbing, followed it like a cloak. It drifted opposite the solar wind, perfectly synchronized with the object's every move. They called it the plasma shadow, and within that shadow, the last confirmed radar reflection disappeared completely. By the second week of November, the name had spread quietly through encrypted scientist forums and dark data channels. Plasma shadow. The phrase wasn't poetic, it was literal. An invisible wake trailing 3i Atlas, bending the solar wind in defiance of physics. It shouldn't exist, and yet it was measurable. The first detection came from the solar orbiter's SWA, Solar Wind Analyzer, which recorded a local drop in proton density as the object exited perihelion. At first, analysts thought it was a calibration error. The Sun's magnetic field fluctuates constantly, and data gaps aren't uncommon. But this wasn't noise, it was structure. The plasma density didn't fade randomly. It fell sharply along a straight edge, then remained low for hours, forming a distinct boundary, a void moving with 3i Atlas. In effect, the object was carving a hole in the solar wind. To produce such an effect naturally would require a magnetic field of immense power, yet no magnetometer detected any field lines emanating from the object. The plasma didn't bend around it, it ceased to exist behind it. That absence, pure vacuum in a region that should have been saturated with charged particles, became the defining signature of the plasma shadow. When the Chinese ASOS observatory independently confirmed the anomaly, the data matched perfectly. A region roughly 9,000 kilometers wide, aligned opposite the Sun, moving at identical velocity to 3 Atlas. The void persisted even as the object's apparent rotation shifted, suggesting it wasn't a trail of exhaust or gas, but a stable zone of influence, an engineered pocket where solar plasma simply couldn't penetrate. For weeks, physicists struggled to explain it. Magnetic shielding was the obvious guess, but the symmetry was too perfect. The boundary line was razor sharp, one side alive with high-energy ions, the other completely empty. Plasma doesn't obey hard edges, it diffuses. Something was enforcing the separation, actively maintaining it. When the Max Planck Institute for Solar System Research ran magnetohydrodynamic simulations, they found that to create a void of that scale, 3i Atlas would need to emit a counterfield of charged particles tuned precisely to the solar wind's velocity. In other words, it would have to sense the plasma flow and respond in real time, adjusting continuously to cancel it out. That kind of adaptive feedback system exists only in theory, in designs for magnetic bubble spacecraft. The implications were staggering. If 3i Atlas was doing this deliberately, it was effectively invisible to the Sun, insulated from radiation, drag and heat. It could survive indefinitely near the corona. But the strangest part wasn't the void itself, it was what the void seemed to contain. On November 7th, the European Space Operations Centre released a preliminary analysis of radio propagation through the plasma shadow. Signals passing behind it, whether from the solar orbiter or background quasars, didn't just weaken. They disappeared, then reappeared moments later, phase shifted by a small but measurable delay. Light wasn't blocked, it was bent. The void acted like a gravitational lens, but one generated by geometry, not mass. That discovery changed the conversation overnight. If the plasma shadow could refract light, it wasn't just empty space, it was structure, perhaps a shell of ionized particles held in precise formation, operating as a cloaking field. To some, it was the final piece in the puzzle. 3i Atlas wasn't merely reflecting sunlight or emitting radio signals, it was engineering its own environment. By this point, the official data lock had hardened into silence. Public-facing solar wind feeds were scrubbed of anomalies, replaced with generic readings, but fragments still leaked through. A team at the Indian Institute of Astrophysics compared old pre-lock files with newly published ones and found something shocking. The background plasma density values had been rewritten. The numbers weren't just smoothed, they'd been recalculated from scratch. Someone was editing the Sun. Privately, scientists shared whatever they could. Among them was a researcher from Kyoto University, who uploaded anonymized differential data, showing that the plasma void followed an almost perfect logarithmic curvature, the same spiral pattern seen in the radio harmonics. The shape was too consistent to be coincidence. Whatever generated the shadow was following the same mathematical template as the 8.4 GHz signal. If that's true, it means the plasma shadow wasn't just a byproduct, it was communication. The object wasn't emitting a signal through space, it was writing it directly into the Sun's plasma. The idea spread like wildfire through encrypted chats. 3i Atlas was modulating the solar wind itself. At CERN, a small group of plasma physicists ran test models of resonant feedback between electromagnetic fields and ionized particles. They found that if a field oscillated at a precise ratio of the Sun's base frequency, roughly 137.5 MHz, it could induce standing waves capable of forming cavities in the plasma. Those cavities could in theory act as mirrors, bouncing radio energy through the solar environment. The object's 8.4 GHz frequency was exactly 61.2 times that base resonance. The ratio was perfect. It was as if 3i Atlas had tuned itself to the Sun's own harmonic. For the few scientists who still dared to discuss it openly, That discovery raised a terrifying possibility, that the object wasn't just surviving near the Sun, it was using it, harnessing the star's field as a transmission medium, perhaps even as a power source. Meanwhile, strange effects began to appear on Earth. A handful of radio observatories reported unexplained interference bursts at sunrise, faint 8.4 GHz pulses reflecting off the ionosphere. Each pulse mirrored the timing of the object's known modulation pattern. To most of the world, they were imperceptible. To those watching closely, they were a reminder that whatever was happening near the Sun was beginning to bleed outward. By November 9th, the plasma shadow had become a permanent feature. Instruments tracking the solar wind through the region now showed a consistent low-density corridor, stretching millions of kilometers behind the object. Within that corridor, plasma behaved differently, slower, colder, almost still. The shape of that corridor was mesmerizing, a twisting ribbon that expanded logarithmically as it moved away from the Sun, its edges pulsing faintly with oscillating charge density. To visualize it was to see a structure, something vast, delicate, alive, and then came the most chilling detail. Embedded within the plasma shadow, the solar orbiter's magnetometer recorded tiny fluctuations, micro-oscillations repeating every 1.37 seconds. When those oscillations were converted into sound, they formed a tone identical to the earlier coded noise sequence, the same prime number rhythm, the same amplitude spacing, but slowed and stretched as though echoing through a medium. It was the same signal, but deeper, slower, resonating through plasma instead of vacuum. No one could say what it meant or whether it was meant for anyone at all. But those who studied it closely began to suspect that the plasma shadow wasn't just a side effect of the object's motion, it was the message itself. Because in every measurement, radio, optical, plasma, thermal, the pattern was the same: symmetry, primes, ratios, repetition. A system unfolding according to law, not chaos, a code perhaps, written in the language of the Sun. And then, on November 10th, everything went quiet. The radio pulses stopped. The plasma density returned to normal. The corridor behind 3i Atlas collapsed in on itself like fog closing over a path. For a brief moment, the object reappeared in visible light, a small cold glint against the Sun, and then faded completely, its reflective surface turning black. It hadn't exploded, it hadn't left, it had simply gone invisible. When observatories recalculated its orbit, they found one final deviation. 3i Atlas was no longer moving away from the Sun. It was curving inward again, descending toward the ecliptic, slowly, deliberately, as if following an unseen path. The plasma shadow was gone, but its pattern, the ratios, the harmonics, the silence, remained etched into every sensor that had touched it. A ghost of order in a universe that should have been random. And what replaced the shadow, faint but undeniable, was a new point of emission, smaller, sharper, directly aligned with Earth's orbital plane. In the quiet after the shadow collapsed, telescopes all over the world turned to the same coordinates. The Sun was calm, the plasma field restored, and yet something about the region felt wrong. The light coming from it shimmered, not visibly, but in data. Photons arriving from the direction of 3i Atlas seemed to slow, to hesitate, as if space itself still remembered the shape that had passed through. Then came the first radar echo, weak, delayed, but clear. A single return pulse from the Goldstone Deep Space Network, a reflection where, for the past 48 hours, there had been only silence. The signal came from slightly below the plane of the ecliptic, about 0.93 astronomical units from the Sun. That was unexpected. 3i Atlas should have been above the plane, receding toward interstellar space. Instead, it had dipped downward, aligning itself with Earth's orbital path. At first, analysts suspected a mirage, ghost data bouncing off plasma turbulence, but the echo persisted. Every 6 hours, it returned from the same coordinates, creeping closer to the orbital plane. The drift was slow, deliberate, constant. 3i Atlas wasn't leaving, it was descending. Within days, the new trajectory model began to take shape. The object's outbound curve had bent into a shallow elliptical arc, crossing the ecliptic at roughly 1.05 astronomical units, just beyond Earth's path around the Sun. By every rule of celestial mechanics, this was impossible. An interstellar object moving at tens of kilometers per second cannot simply settle into orbit. It doesn't have enough time or energy or atmospheric resistance to bleed speed, unless, of course, it does it intentionally. The revised orbital parameters showed a progressive loss of velocity, small but measurable, about 2 meters per second per day. It was as if 3I Atlas were applying brakes, decelerating gently, tuning itself to the rhythm of the planets. The curve projected forward by simulation intersected Earth's orbital zone around June 2026. That single number, June 2026, set off alarms in every agency still quietly monitoring the object. Within 48 hours of the new model circulating, the data was withdrawn. NASA replaced its public orbital table with a static archival version dated October 25th, before the Perihelion. ESA's heliophysics portal redirected to a maintenance page. The Minor Planet Center deleted its tracking logs entirely. From the outside, it looked like 3I Atlas had vanished, but internally analysts knew the truth. The object hadn't disappeared. It had changed course toward the inner solar system. The decision to lock data was immediate. In early November, a joint task group was formed under the name Project Horizon, combining personnel from NASA, ESA, and several defense agencies. Officially, its mission was orbital clarification. Unofficially, it was containment of data, of speculation, of fear. Among the leaked briefing notes later posted anonymously to academic servers, one line stood out: trajectory adjustment consistent with guided maneuver, origin of force unknown, re-entry vector currently intersects ecliptic at 0 degrees declination. In other words, 3I Atlas was aligning perfectly with Earth's orbital plane. The shift wasn't violent or abrupt, it was graceful, subtle corrections timed with solar flux, using only sunlight for propulsion. Each adjustment coincided with a faint optical flare, the same mirror-light pulses observed weeks before but now subdued, almost whisper-like. The reflections appeared at 12-hour intervals, symmetrical around the solar vector, as though the object were fine-tuning its orientation. Independent observers tracking it through private telescopes described it as drifting with intent. For weeks, every new positional update added to the strangeness. The object's apparent magnitude remained constant despite changing distance, a sign that its reflective area was compensating for solar angle. Its thermal emissions, too, were stable, a flat minus 70 degrees Celsius, unaffected by solar proximity. It behaved like a craft maintaining steady internal control. Meanwhile, whispers circulated that radar operators were noticing something even more peculiar: shadow returns, duplicate echoes offset by microseconds, like reflections from multiple layers of the same object. When mapped, those echoes formed a faint ring pattern around the primary signal, as though 3I Atlas were surrounded by concentric shells of ionized gas. Those rings matched the scale of the plasma corridor that had collapsed days before. It was as if the structure hadn't vanished, it had condensed, shrinking inward around the object like armor. One hypothesis began circulating among classified groups, that 3I Atlas was preparing for a long-duration orbit, not a flyby, not an escape, but residence. The math supported it. If the deceleration continued at its current rate, the object would achieve orbital insertion by early 2026, circling the Sun every 14 months, roughly synchronized with Earth. The two orbits would intersect once per cycle. When that projection leaked, governments scrambled to suppress it. The implications were too unsettling. A foreign probe, if that's what it was, establishing a solar orbit parallel to Earth's? Too many questions, too many strategic risks. Inside Project Horizon, however, panic gave way to analysis. The object's movement was too elegant, too consistent to ignore. Engineers began modelling the possibility that 3I Atlas was using solar radiation as both energy and propulsion, a kind of light drive equilibrium, capable of indefinite motion without fuel. That concept existed only in theory, proposed decades ago under the name photon sail stability loop. But 3I Atlas appeared to be demonstrating it. As days passed, a new detail emerged from reprocessed data. When the object's path was extrapolated backward, the line didn't originate from interstellar space. It originated from a point along the Sun's northern magnetic pole, inside the corona. Whatever 3I Atlas was, its arrival had begun within the solar field itself. The possibility that it had not entered the solar system from outside but activated within it rewrote everything. By November 15th, internal telemetry suggested the object's acceleration had stopped completely. It was now moving in perfect harmony with the ecliptic, parallel to Earth's orbital velocity, trailing the planet by roughly 31 million kilometres, a stable resonance point known in celestial mechanics as a co-orbital Lagrange drift. If it stayed there, it would remain permanently hidden from direct observation, always on the far side of the Sun, its trajectory matching ours. That is, until the alignment shifts, when Earth and the object's orbital paths bring them briefly into mutual visibility around March 2026. Until then, the Sun itself acts as a wall between us and it. Publicly, 3i Atlas was forgotten, relegated to archived press releases and quiet dismissals. But in private briefings, analysts continued to watch the numbers, noting that every 46 minutes, deep space receivers still caught a faint pulse at 8.4 GHz, a heartbeat echoing through the void. Whatever 3i Atlas is doing, it hasn't stopped. It's only moved out of view. And every model, no matter how constrained, ends the same way. By June 2026, the object crosses the ecliptic on the near side of the Sun, within visual range of Earth for the first time since Perihelion. No one knows what will happen when that day comes, but the silence, the patterns, the precision, they all suggest the same unsettling truth. It isn't gone, it's waiting.